One last graphical thing I am going to do is just change the scale of the skeletal mesh here to be slightly larger, maybe 0.55. See what that looks like, just so that there is less gaps between them when they are present on the board, so that the player is still like, oh, okay, those are still like a contiguous block. Let's see if I can make that a little bit bigger. Did I even compile last time? I'm not sure. Okay, that's probably good. Whoa, didn't mean to do that. F3, I think will bring everything back. F3. I wanted to pause and eject and look at what these look like. Not too much Z fighting is what I'm trying to prevent here. I don't see any noticeable Z fighting. So that's good. Now, on to the clearing logic. So once the timer bar has reached the end. Okay, actually what we can do is either once the timer bar has reached the end here, and we reset its position. Before we reset its position or after, doesn't really matter, but I'm going to do the position last. I want to, clear all of the highlighted blocks. So I can do that by either just finding every single block in play again, doing a find all actors of class, and then just checking each one to see if it's highlighted, and then calling some sort of delete function on it, telling them to delete themselves, destroy themselves. Or I could add these references to an array as I go. That way I won't have to call that get all function again here. Well, if we call, find all actors of class or get all actors of class once per, cycle of the timer bar, that's probably negligible performance. That's probably like fine. So if I was squeezing every ounce of performance out of this project, I would make a new array to hold all the blocks to be cleared, and I would destroy them that way. I might still do that anyways so that I can, we'll just do this for now. It should be a little bit quicker. So, quicker to create, perhaps not quicker at runtime, but just get all the blocks that are in play right now. And for each in the array, we're going to do something. And after we're done with that loop, we're going to move the timer bar itself back to starting position. And what we're going to do here is just say, are we valid? And get my state. So if this is valid and its state is highlighted, then what we want to do is we're going to call a special function on them, telling them to destroy themselves, basically. But first they're going to, let the game know that they're being destroyed, increment the score by some amount based on how many matches they are a part of. But for now, we're just going to have them destroy themselves, probably. So let's quickly make a function on the block. Call it clear self from the board. That's not a very good name for it, but what it entails is this function does everything that needs to be performed before this block gets destroyed and removed from the game, including destroying self. So not only does this call destroy actor on self, it's going to do any cleanup it needs to do beforehand. You know, like notify the game mode that it increased the score and so on. But for now, all it's going to do is destroy itself. I don't know if we need to put a return node here, if it'll even get to that point, but I know destroy actor doesn't immediately destroy. You know, it marks it for deletion, and then at the end of the tick, it gets destroyed. As far as I know. So we're just going to call clear self from board on this current element if it is highlighted. So I'll move everything down a little bit to give myself room for the wires. And we'll see how that works. Now hopefully when the timer bar reaches the right hand side, anything that's been cleared, marked for clear by becoming highlighted, will then be actually cleared from the board. So they're highlighted now, and then they're cleared from the board. Cool. So no warnings or errors. I think I'm going to actually slow down the transformation into a cleared block or a highlighted block, because I want that to happen as the timer bar moves through the whole entire block, not just like as soon as it touches it. So let's make this like 1.25 seconds instead of half a second, maybe 0.8 seconds or something, so it's not so ridiculously long. Now, the final piece of this clearing puzzle is we need to drop all the blocks above the cleared blocks. So like in this case, there's only going to be one that needs to drop, right? It's going to be this block right here. It needs to drop down to here after the ones below it got cleared. So what we need to do is just have an algorithm that gets every block, and this needs to happen actually by row, because if you think, say there was 2 blocks here that needed to fall down all the way, they each need to fall down 2 rows, right? But if we had this block fall, if we had the block above it fall first, it would stop falling immediately because there was a block immediately below it. So we need to clear the bottommost row first, make sure they've all dropped as far as they can, and then we go up 1 row and make those blocks all drop as far as they can, and then repeat that process for every single row that might have active blocks inside of it. So to accomplish that, we'll need to either get all blocks using the get all actors of class function, and then sort them by height, and then do each of those height arrays, do it like perform a drop function on each height array sequentially, from the bottom row to the top row. That could work, or we could do an actual ray trace, like do 10 distinct ray traces and grab all the blocks that we find in those ray traces and then drop them all down. That may be cleaner. It may be less performant, or maybe more performant compared to, get all and then sort them by height. I think either way should be fine. I think I'm going to go ahead and try the ray traces method though, because that way we don't have to like store all of these in one big array and then make 12 or 10 new arrays and then loop through those arrays, or do like a nested for each loop or something like that. So let's instead just do 10 distinct ray traces, and after each ray trace get all those results into an array and call the drop function on all of them. We actually don't need to do that on the bottommost row, because if there are any remaining blocks in that row, they don't need to drop at all. So we just need to do 9 ray traces, 1 for each of these rows. And then starting here, the order is important, right? Because we have to check here and then drop, and then check here and then drop, and then check here and drop. So they don't have a weird instance where a block gets stuck on a block that itself hasn't dropped. So let's go ahead and get that working. So I think this is something we'll do in the game mode. We'll make a function called drop all blocks to fill gaps. So called when the timer bar clears all of the highlighted blocks. So we're going to do a get all actors of class. No, we're not going to do that. We're going to do the ray trace thing that I was talking about. So to do that, we're going to do a for loop. Oops. So for loop from, so the index is going to represent which row in the grid we are currently ray tracing through. So we're going to start at index 1, which is going to be the first, like if this is the 0th row, this is going to be row 1. I'm going to start at 1, and we're going to either go, the last index is going to be num rows, or num rows -1 or something. We'll see how far it's going to go and adjust the iterator accordingly, the condition here. So we're going to do a multi-line trace, so multi-line trace for objects. And the start and end are going to be based on the index value. And this is going to be 0.5 because we want to go into the center of the grid slots, right? So right now we're aligned with the lines themselves. We want to go into the center of the rows slots and go along the middle of it to trace for our blocks. So we need to go half of a offset plus whatever the index currently is. This many vertical offsets, so this number times vertical offset. We might want to just do this relative to the grid in case we do move the grid later. Right now it's going to be world space, but we might as well do it in grid space by adding the location of the grid to this. So I think at one point I had a grid variable here, and I don't any longer, so I'm going to put that back in and do grid BP reference. And when we add the grid at the beginning here, we're just going to set that reference. I think I said back when I removed this that we probably need it eventually, so I should have just left it to begin with. There we go. What am I doing wrong here? Oh, yeah, okay. So now we have the grid. We get this actor's location, which is going to be 0, 0, 0 right now, but just in case it's moved later. let's set this up dynamically. So this is where we're going to start and end our line trace offsets. So this is like the reference point for our start and end. And we add this Z offset to it. I don't know if it's going to be neater looking with vectors and conversions to and from vectors, or just using all these floats, but for now I'll just try floats. So X and Y are going to initially be 0, and this is the starting Z offset. And it's also the ending Z offset, and Y is still going to be 0 at the end. But for X, we need to go to the right-hand side of the grid and end there. So we need to go from the left-hand to the right-hand side of the grid. The starting X value plus, yeah, you can already see this is a bit of a mess. Yeah, let's try converting these back into vectors before we insert them into the line trace node. So recombine these. That way we can give it just a bit of space visually. So again, X and Y would be initially 0, and Z is the offset for starting and ending. And then for the Y, it's the same. Kind of bundle them up visually. And then for the X ending position, it's going to be this value plus a float, which is going to be horizontal offset times an integer, and that integer is just going to be number of columns. And that, we need to adjust that by 1 in either direction. But for now, we'll see where we end up when we do that. So again, we need to make an array here. So object types, as we've done this a couple times before, just left click here, do eObject type query. It needs to be an array, so I'm going to right click this to make it an array, and then set just one element as a default value, world dynamic. Plug that in here. That should finally get rid of that error. And actors to ignore. We want to ignore the grid itself, so we don't get the collision boxes. Make an array of one element here. Get our grid reference so we ignore the grid when we're doing this. And this is just getting really clogged up, isn't it? Try to keep it relatively clean here as much as we can. So now I just want to visually look at this line trace and see what's happening. And clear this log. And after we have completed our clearing of all the highlighted blocks, we're going to tell the game mode to run that function. Drop all blocks to fill gaps. And right now it's going to do, hopefully, a bunch of lines through the middle of all the rows. Oh, this is not the right thing. So if this logic is correct, that's what it's going to do. And if it's not correct, then I will fix it. Okay, as you can see, I am off by 1 here, but otherwise it seems to be working properly. A multi-line trace doesn't turn green when it finds its first collision, but you can see there's collision boxes here, but we're going to need to exclude the quad from the list of things that we're looking at. Otherwise, we're going to force the quad to drop down when the player is currently controlling it, and they don't want that to happen, obviously. Num rows -1. And we don't need that bottom row because there's no need to try to make the blocks that are along the very bottom row drop because they can't drop. So just check every other row except that one. This is not straight, so I'm going to make it straight. There we go. And so this is an array of hit structs. So we're just going to do for each loop. And then we need to break the struct here. Wow, we don't need all this data, but all we need is the hit actor and cast to block BP. If the cast is successful, we just need to call the drop function on it. And that drop function is going to be discrete from the current drop function we have for the quad. Right now we have somewhere in the player controller, it's the move left half down and move right half down. We don't have a quad to move the halves of, we're moving a specific block. So we could do this in the player controller, but since the player, that wouldn't really make any sense because the player isn't the one controlling these blocks, it's the game is just making these blocks fall. So this should happen in the block logic. That would be more logical, I think. Got a bunch of tabs here. I'm just going to close all these tabs except the event graph. So I'm going to make a new function called drop as far as possible. When called, this block will drop 1 space at a time until it encounters an obstacle below it. Either the bottom of the grid or another block. We can make them drop 1 space at a time, but that'll involve a lot of timers and logic to make them move gradually down. And we want them all to drop down. We want all the blocks to drop down in unison. If we want them to appear as they're falling with gravity or falling 1 space at a time, we need to set that up carefully. So what we can do instead is just have them drop immediately to the bottom. Okay, so after watching the YouTube clips of the game, the real game being played, I have made some realizations that will require some refactoring of the logic we've set up here in the timer bar. So in the real game, once the timer bar has gone across a contiguous series of matched blocks, it will keep highlighting blocks until it stops highlighting any more matched blocks. So what I mean by that is, as soon as the timer bar keeps going through these blocks and then gets to this column and says there aren't any matched blocks in this column, so I'm going to stop highlighting and I'm going to clear all the currently highlighted blocks. So what would happen in the real game is the timer bar will continue through these highlighted blocks and say, okay, there's some highlighted blocks. Okay, this column has some highlighted blocks, I'm going to highlight them. And then it does that, and then it says, or rather it says this column has some matched blocks, so I'm going to highlight all the matched blocks. And then it comes to this column and says, oh, there are no matched blocks in this column, so that's the end of this sequence of highlighted blocks. So I'm going to clear all the 4 highlighted blocks that I've highlighted so far, and then all the ones that were above those get cleared and I get dropped down. So it's a discrete concept from the combo system, which after these 4 were cleared, the number up here in the real game would say like 1, which means there's 1 match from this cycle. So basically what I'm getting at is I've structured some of this incorrectly. So where we have the timer bar, reach the end and then clear all highlighted blocks, that's actually not what we should do. We should check each column as we enter it. As the timer bar enters a column, it should check all blocks in that column and highlight them or ignore them appropriately. And then as soon as it reaches a column where there aren't any highlighted blocks, it needs to check its array of currently highlighted blocks and delete all of those, and all the blocks that were above in those columns need to get moved down. And there's some elaborate particle effects when highlighted blocks get cleared in the real game, which sort of mask what happens underneath, but it looks like the blocks above the highlighted ones do drop down gradually to fill the gaps, but because there's like particle effects, it basically just seems like they instantly go to their destination. It's very quick, so we're probably just going to have them instantly reach their destination. So we're going to need some sort of data structures to hold the results of each column check. So I think instead of, we may not even have to do this whole ray trace thing that we just spent 10 minutes setting up, but we need to, instead of doing that ray trace for all the different, hanging, floating blocks and dropping them, we instead need to keep track of every block in the columns where there were highlighted blocks, so that when we clear highlighted blocks, we can ray trace upwards from the cleared blocks that are getting destroyed and find all of the blocks that may or may not be, or that may be there. And if they are there, then tell them to drop down as far as they can. So I think we need an object associated with every single column. That would be a simple way to do this. And that object gets interacted with by the timing bar. And when the timing bar touches that object, it'll say, okay, look at this column and tell me how many matched blocks there are in it. If there are matched blocks in it, then I'm going to make them highlighted. If there are no matched blocks in it, and I have a non-empty array of existing highlighted blocks, then I need to destroy all those highlighted blocks. So a bit complicated in my explanation, I'm sure, and it's going to require certainly some refactoring, and then also a new approach to finding which blocks to drop. But this is kind of the crux of the entire project, is getting the blocks to drop properly. So it's certainly an important step, and probably the most complicated step that we've had to encounter so far in terms of the logic and planning and algorithm. But that's what makes it so exciting. So hopefully we can come up with an elegant solution that will not cause a weird stutter step with the blocks above them. It won't attack the quad and rip it in half. Like right now, if we had a column look up here and say, okay, find all the blocks above this highlighted block and pull them down, it would pull the quad down, which we don't want. So we should ignore the quad, and we do still need to do them from bottom to top, and that leads to another very tricky situation. What if there was another group of highlighted blocks here between, say these were orange and these were all silver, and then we had another set of silvers here, so we had 2 squares of highlighted blocks that needed to be cleared, but then we still need these 2 to fall down, and we also need the ones above them to fall down. So the ones above them would fall down, 4 spaces because there were 4 gaps created. And this guy would only fall down 2 spaces because there are only 2 gaps created. So perhaps instead of looking down, looking up, we could have every block in the column look down and determine its own number of slots that it must drop. So like instead of doing a drop at a time, we'll have each block determine for itself how many blocks it needs to drop to reach the next solid object. And if we do that from bottom to top, then we'll know that everything underneath that solid object is also either the bottom of the grid or a solid object itself. So that's going to require some thought and some clever algorithms, but it should be pretty fun. So let's get to it.